thermosets. Okay, elastomers. We will be talking extensively on elastomers later in the semester as well, because we will have a separate chapter on elastomers. What I want you now to remember regarding the elastomers is that they can extend a lot, okay, because they have very light crosslinks, okay? The amount of crosslinks between the chains in elastomers is very small, and that allows them to elongate a lot by stretching their chains, okay? It is very important that because of this light cross-linking, these materials are very soft, okay? And because they're very soft, they can elongate a lot and they display a low modulus. Their modulus is in the order of 0.1 to 10 megapascals. Some characteristic examples of elastomers can be, can be, let's say, natural rubber, can be nitrile butadiene rubber, can be polydimethyl siloxane, which is which has silicon and oxygen atoms in the main chain, as we said, so that makes it extremely soft and so on. Okay, so elastomers are mainly amorphous materials. So that means that they have a random structure of their macromolecular chains, okay? So this is random structure, arrangement, call it whatever you want, okay? Now, besides elastomers, we have thermoplastics, which are very, very interesting, okay? And they display both crystalline and amorphous regions, okay? So we have both. I forgot to mention that elastomers, because they are mainly amorphous, they don't have a melting point, okay? They have only glass transition. Thermoplastics, on the other hand, we say that they are both crystalline and amorphous, okay? Because they're amorphous, they have a glass transition, but because they're also crystalline, they have a melting point as well, okay? So thermoplastics, so both a melting point and the glass transition. And we will see how these two thermal transitions are following each other sequentially when heating up a polymer or cooling it down. Yes, so thermoplastics, they are composed of long chains and produced by joining together monomers. That is the process of polymerization. And typically they are ductile, okay? Ductile means we can bend them, we can stretch them, but it is important that if we stretch them, we don't overcome the plastic deformation, okay? Because if we get plastic deformation, then we have permanent deformation, and thermoplastics cannot return to their original shape or dimensions. Okay. Apologies for the coughing. I'm a bit sick. The chains may or not may have branches. We talked about the effect of branches in the previous class, where we said that branches can essentially guide how chains slide against each other, and also what is the relative distance between chains, and the amount of branches also dictates the crystallinity of the materials. A characteristic modulus of thermoplastic is in the order of 1 to 2 gigapascals, and some thermoplastics can be polypropylene, polyethylene, polyvinyl chloride, and so on. Okay. And finally, we go to thermosets. Okay, thermosets have long chains, but they are very strong cross-linked between them. Okay, so they have many points here of cross-linking. You see, there are so many regions where chains cross each other, but they are bonded. Okay, these are formed by chemical bonds, and because these are chemical bonds, these are very strong to break, and that is why thermosets are very stiff. Okay, so yeah, they are strongly. That is the key word here. They are strongly cross-linked to each other, and they form 3D network structure. Okay. Thermosets also show very, very low crystallinities, so they are mainly amorphous as well. So they usually don't have a melting point. So they have a glass transition. So if they have a glass transition, they just soften above the glass transition, but they don't melt. Okay, and in this case, the modulus of thermosets is 3 gigapascals and over. Some characteristic thermosets obviously are epoxies, okay? Epoxy resins, the way we call them, okay? So let's look a bit more onto the different types of thermal transitions, okay? In terms of the glass transition, I want you to remember that the glass transition is related to the thermal energy that is required to allow changes on the conformation of the molecules at the microscopic level, okay? And by saying a conformation of the molecules is giving enough thermal energy to the molecules in order to start moving, to the macromolecular chains in order to start moving. Because when they're in the glass state, the chains, as we said, they're entangled with each other, okay? So they're frozen. They don't move. But when we provide them enough energy, we change the conformation of these macromolecules. And because we change the conformation of these macromolecules, we make the chains move. We give them vibration energy. And because this vibration energy makes them move, then these chains can slip against each other and they start moving. And then we surpass the glass transition where from a very stiff material, we will move on to a much softer material. So what we need in terms of the glass transition during heating is to provide them with enough thermal energy. Okay, so if we look first upon heating, the glass transition is defined as the temperature at which there is enough energy for rotation around bonds, about bonds, or whatever. So again, we want thermal energy to allow changes in the conformation of the macromolecules. We want energy to make the molecules move, because below the glass transition, the chains are frozen. Okay, the chains do not move at all. So they're locked in there, and because they're locked in there, the polymer is stiff. It is hard. But when we provide thermal energy to the chains, when we heat it up essentially, we make the molecules move, and then there is enough energy for rotation around bonds. Also, we can observe the glass transition during cooling, okay? So during cooling, when the melt of a polymer is cooled, it becomes more viscous and flows less readily. If the polymer is not able to crystallize and the temperature is reduced low enough, it becomes rubbery, and as the temperature is reduced low enough, it becomes a hard polymer glass. So the temperature at which the polymer undergoes this transformation from a viscous melt to a stiff polymer glass, it's called the glass transition temperature. So the temperature at which the amorphous domains of a polymer take on characteristic glass state properties: brittleness, stiffness, and rigidity. So you know how a glass is, right? You can break it very easily if you apply deformation. So if you very quickly bang on a glass, it will break. So it is brittle. But if you press it like that, it's very stiff, it's very hard. So that is the two characteristic, let's say, properties of a glassy-like material. When you apply soft energy, soft deformation onto the glass, it's stiff, you experience it stiff. But when you apply a very hard, very quick deformation, then you can break it, and that gives brittleness to the glass, okay? So this is a definition for the glass transition temperature. I should point out that two things. Firstly, there is not one glass transition temperature for a polymer, but there is a temperature range, okay? So we can say, okay, we will be defining a glass transition, let's say a TG of around, I don't know, minus 10 degrees for polypropylene, but in this order, in minus 10, we can have either minus, I don't know, 15 to minus 5. It doesn't really matter. It is generally a temperature range. Of course, in order to establish a single temperature, we apply, you will see how do we define in an experimental case the measurement for the glass transition, but generally TG is considered a temperature range. The same applies for the melting point. And also, it's obvious that TG is a property okay. So whenever we observe something with regards to TG, this has to do with the amorphous part of the structure of a polymer. If for the crystalline part, then we have the melting and the crystallization temperature. And what is the melting? Simply, the melting temperature is the temperature at which the crystalline domains of a polymer are destroyed, okay? So the melting point is the melting temperature of the crystalline domains of the polymer sample. So it has to do with the crystalline regions. Crystalline regions, we will see later that they are packed like that. So they have a high degree of order. Of course, there is a crystallization temperature, that is the melting point. We have the crystallization temperature, TC, which is the temperature when a semi-crystalline polymer from a liquid state is cooled down and it solidifies at a certain temperature. This temperature is called the crystallization temperature, okay? And then we have also some secondary transitions, such as these are called TAF beta or TAF gamma. These are not too important. We will see later about secondary transitions. They are not, as I said, they're not too important. These have to do with the movement of the side groups or some very small movements at low energies, but they don't affect significantly the properties of the polymer, so we won't be looking into them very carefully, okay? Something very important that I write here is that the operating temperature of polymers is defined by their transition temperature. And of course, you can realize that for the melting point, if we start with melting point, if we want to process a thermoplastic by, let's say, melting it and forming, I don't know, forming a shape like that, let's say. If you want to form a shape like that, you first have to melt this material. What is this? Is this polypropylene? Must be polypropylene. So if you want to, you have to first melt it and then do another process that is either injection molding or extrusion. The glass transition is the temperature, as we said, that the material softens significantly. So from a stiff material, it becomes very soft. So the way we will experience a material, whether if it's soft or if it's stiff, it depends on its glass transition temperature, okay? Now, if we look upon these graphs of volume versus temperature, for amorphous materials, we said already that we have only glass transition, okay? And in this case, we have, because they are amorphous, we have a random molecular structure. We said the other day, in order to consider a random molecular structure, think of cables behind your television or cables behind your desktop or whatever. They are completely entangled, okay? They are entangled. So there is no regularity in the structure. And because there's no regularity, these are amorphous, okay? They have no crystallinity or tiny amounts of crystallinity, which may be random, okay? So in this case, when we increase the temperature for an amorphous material, we pass from the glass state to a softening point, which is the glass transition temperature. And then we go on to a liquid state or a very highly viscous state, let's say. Does anyone remember what we said it is the viscosity? Can you send me a text in WeChat? What is viscosity? Let me open WeChat. I think I have it on mine. Do you remember we said it the other day? No? Okay. Viscosity shows us how easy a substance flows, okay? So if I give you an example, water has a very low viscosity. On the other hand, someone said, yes, the resistance for a liquid to move is well high. So essentially, water has very low viscosity, while honey or I don't know what else, Nutella, let's say, or something like that, or maybe ketchup have much higher viscosity. Okay. So in the case of amorphous materials, we pass from a glassy state to a liquid state. For crystalline materials, what did we say? We said that we have an ordered molecular structure. Of course, it is, as we said, it is very hard to obtain only crystalline material. It is very rare to see 100% crystalline polymer, okay? So in crystalline materials, we have ordered molecular structure. The chains look like that. They fold upon each other. We will look on the next section upon the models of describing the folding of these materials. And in this case, when we go from a solid, when we hit a solid polymer, a solid crystalline polymer, we go through the melting point and we have an important increase in volume in order to produce the liquid state, okay? We will see later when we will characterize the thermodynamics of the thermal transition. This is a first order transition, while previously the glass transition is a second order transition. Don't worry about it now. I will explain more either later today or tomorrow. Of course, now we looked at the two extremes, okay? We have only amorphous and only crystalline. Obviously, there is the case of thermoplastics, again, which we said that we have the semi-crystalline material. Let me use another color. For semi-crystalline materials, we have both Tg and the melting point, okay? These temperatures are obviously different, very different. They have a very large temperature difference between the two of them. So if we compare an amorphous or a crystalline material, sometimes amorphous materials can be also called glassy, okay? Let me make a note here. So anytime you see as glass here, I don't mean a real glass, but I mean an amorphous material. So what is exactly here what we said earlier? From for an amorphous materials, we go in this direction and then passing from the glass transition, we have a change in the slope, okay? That is why we call it a second order transition, because we have just a change in slope. Well, in the first order transition, you see that we have a very high jump, okay? So because of this jump here, this is a second order transition. First order, sorry. Jump. As you can easily realize from this graph, we have a much higher volume for the case of the amorphous material compared to the crystalline material, okay? And that is relatively easy to realize, because if you have, let's say, if we have two chains, let's suppose we have two chains. For a crystalline material, two chains can look like that, okay? They are very tidy, they're very like ordered and so on. These chains for an amorphous materials can be like that. So you can realize they can occupy much larger volume, okay? And that is why in this case, VE here is higher than VF. So a crystalline material shows lower volume than an amorphous material. And obviously, you've seen it. If you freeze a material that's crystalline, it shrinks. Okay, so here we can say that we have shrinkage due to freezing. Okay. So what did we say so far? We have two major types of thermal transitions. Okay, we have the melting point and we have the glass transition temperature. Above the melting point, the polymer is liquid. It can be viscous liquid, but it is considered a liquid. Okay, and below the melting point, we have a flexible crystalline solid. Okay, consider polypropylene, polyethylene. So we have a material that can essentially be pliable, be, let's say, easily processed, and has some crystallinity in there. For the glass transition temperature, though, we said that above the glass transition, the materials become soft, okay? They become rubbery. By saying rubbery, in this case, we mean soft, okay? So from stiff, they become softer. And below the glass transition, the polymers become glassy, okay? So from a soft material, we can obtain a material that is hard, let's say, rigid, or stiff. All these words essentially describe the same thing, okay? Describe a material that is difficult to let's say, difficult to handle in terms of stiffness. And stiff obviously means that it can break very easily if you apply significant force onto it. It cannot extend, let's say. Let's look at some characteristic types of polymers and their transition temperatures. So for high density polyethylene, which we said that it is one of the most interesting engineering materials because we can use it for so many advanced applications. Of course, we said that ultra high density is the most advanced, but anyway. So polyethylene has a glass transition of a minus 120 Celsius degrees, a glass transition. That means that at any point that we experience polyethylene, this material is above its glass transition temperature. That is why it's always very stiff and hard, okay? And that is why it operates very, very well in engineering applications where we need a stiff material, a rigid material. Its melting point, though, if we want to process it, if we want to melt the material in order to give it a useful form for us, that can be any type of application where we use polyethylene, its melting point is 135, okay? Polycaprolactone, which is another interesting material. Minus 60 Celsius degrees, a glass transition, 61, the melting point. So you can realize the polycaprolactone has a very low melting point, but in terms of when we experience it at room temperature, it's still relatively stiff, okay? The same with PVDF, minus 45, a very high melting point, and so on. Polyvinyl alcohol, on the other hand, has a very high. So in this case, it is relatively soft, okay? So these are some characteristic polymers, and from here I'll just introduce what is the difference between the melting point and the glass transition. We said that melting is a first order transition. It has a discontinuity in the first derivative of Gibbs free energy. Okay, Gibbs free energy, it has to do with polymer thermodynamics. We will explain more later. But the Gibbs free energy is a thermodynamic potential that can be used to calculate the maximum of reversible work that may be performed by a thermodynamic system that is at constant temperature and pressure, okay? So Gibbs free energy is the potential that can be used to calculate the maximum reversible work performed from a thermodynamic system. We will see more of that later in this course. On the other hand, glassification, we mean passing through a glass transition, is a second order transition, pseudo, let's say. By saying pseudo, it is not absolutely correct that it is a second order transition. It's not too important, don't worry about it now. What I want you to remember though from this slide, and what is very, very important for you to know, is what happens when we are heating through the glass transition temperature for polymers, okay? That is mostly for semi-crystalline polymers, but generally what happens when we heat through the glass transition. So heating through the glass transition gives us 4 important results, okay? Firstly, we break down the van der Waals forces. Any van der Waals forces between different chains in a polymer, they're broken, okay? There's no cohesion between the chains, okay? Let me write it down. This BTW is between, okay? Just to abbreviate. The second thing is we start, as we said, large scale molecular motion. We said before the glass transition, I repeat it once again, I want you to remember that. Before the glass transition, the chains are frozen. The chains are not moving, okay? Or they have tiny vibrations that we cannot feel it in small scales, okay? In small experimental scales. So because they are frozen, there's no movement between the chains. Then once we start heating up, we have this onset of large-scale molecular motion. So the chains start moving in here, and they start disentangling themselves, and then they completely disengage from each other. Okay? So heating through TG, the second important point is that they go through large-scale molecular motion. It is the start of large-scale molecular motion. The third point, the polymer goes from stiff to soft, from glassy or rigid to rubbery behavior. Glassy or rigid, we said, they have high modulus, and low elongation. To rubbery behavior, that is low modulus, high elongation. Okay? So from a stiff material, a glassy material, we move on to a soft material. And finally, the glass transition is the maximum service temperature in amorphous polymers. Amorphous polymers, we said, they don't have any crystalline regions, okay? And because they don't have any crystalline regions, they don't have a melting point. So we need a temperature at which the properties of the polymer change completely. And that is the glass transition temperature. In this case, the upper surface temperature is the temperature that we experience, let's say, the certain properties of a polymer. If we go through the glass transition, then these properties do not exist, and that is the maximum surface temperature for amorphous polymers. Okay? Now, let's go on to an important graph. From here, I want you to ignore these blue part here. It is wrong. Ignore the blue curve and focus only on the red one, okay? If you see this graph, can you tell me what kind of polymer is this one? If you just see this graph, without myself explaining anything, what kind of a polymer are these? Is this, sorry. Yes, it is a semi-crystalline polymer because it has both, you can see that it has both glass transition and melting point, okay? This is a graph that we generally produce with an experimental technique that is called dynamic mechanical analysis, or DMA. And it gives us the modulus of the material. That is a modulus, okay? It can be the logarithm, it doesn't matter. It gives us the modulus of the material, the stiffness of the material, as a function of temperature. Okay, and that is the way, essentially, the way that we experience that material. So, if we take semi-crystalline polymer, we start from low temperatures. Let's say we start from minus 150, and we start heating it up all the way to 200 Celsius degrees, let's say. Here, at low temperatures, we have the chains that are frozen, okay? We already talked about that. Up to this point, the chains are generally frozen. Or Okay, we can also say that the chains are mainly frozen in this region, but okay, it doesn't really matter. That's why we say the glass transition is a region. Okay, it's not an absolute value. Anyway, in this region, certainly, in this region, we have that the chains are frozen. The chains are not moving in. They're locked with each other. They have no vibration. They have nothing. Even if we increase the energy, there is very, very small onset of movement. But once the chains start being in this region, let's say, the chains start moving, okay? And because they start moving, they find slowly enough thermal energy in order to pass through the glass transition. So first we have this region, which is the glassy region. And second, there is this point where we have the glass transition region, okay? Then after the glass transition region, we reach this plateau here, okay? This is the rubbery plateau, part 3, okay? So after we pass through the glass transition, the chains start to, as we said, to disentangle from each other. But they still have the polymer has still a certain modulus, okay? It's not completely liquid, so the chains slip against each other. So there is some segmental mobility. The chains starting to, with enough thermal energy, they start to disentangle from each other. And that is why I write here that the longer the chains we have, the longer this plateau is, okay? Because the longer the chains we have, the more entanglements we can get, okay? I hope class 208 is okay, because I see there's something loading. I hope the connection is fine. If there is a problem, please text me. I continue. So then with further heating, we go on to the rubbery flow, which is complete disentanglement, and then we have the viscous flow, where we pass through the melting point here, and because there is this viscous flow, the materials are able to flow, the chains are able to flow against each other, and then the material is completely liquid, okay? And because it's liquid, the modulus drops to 0, okay? And that is how we measure the modulus versus temperature for a semi-crystalline material. It is a very useful and very important graph, because it provides us with a number of significant information regarding the transition temperatures, the modulus of our material, and essentially what happens in terms of polymer physics in a polymer when we heat it up, okay? So I repeat once again, we have, at low temperatures, we have the chains, they are frozen. Then we give them a bit of energy and they start moving. And because they start moving, the material softens. It passes through the glass temperature, or the glass transition temperature. Then after it passes the glass transition temperature, the polymer becomes softer. It still has a modulus. And then the more energy we provide, then we have this slippage against the chains, and we pass through the melting point, the chains slip against each other, and here we have a liquid material, liquid state, where we have a viscous flow of our material, okay? Let's take a 10-minute break now, and we can continue with a few more points regarding the glass transition temperature of polymers, okay? So let's get started with the second part of today's class. I realized that the polymers group lost connection for the last 2 minutes or so, or 3 minutes. Well, I didn't say anything that important. I was just repeating the details of this graph, which I said it is very important. Very briefly, I'll just repeat it once again. This is the modulus versus temperature graph for a semi-crystalline polymer, okay, where we can use it to identify the thermal transitions of a semi-crystalline polymer, okay? And what happens in terms of polymer physics when we provide thermal energy to a polymer from starting from a very low temperature up to a high temperature, okay, above its melting point. So when we're at a very low temperature and we slowly heat up the polymer, the chains are still frozen, okay? They don't move against each other. But the vibrations increase between the chains. And then after there is enough thermal energy, we pass through the glass transition temperature, okay? Where we have mobility of the chains, change of conformation between macromolecular chains. So that is point 2. Okay, and then from point 2, with further increasing the temperature, we provide more mobility to the chains. Segmental mobility means macromolecular mobility. And this region here, shown by number 3, it's the rubbery plateau, it's called, okay, because the polymer in this case displays rubbery characteristics, and the length of this plateau depends on when the chains will be completely disentangled from each other, okay? They have no points where they have kind of physical crosslinks with each other. So if we have short chains, it is going to be easier for these to disentangle. If we have longer chains, there are more entanglements, and that leads to a longer rubbery plateau, okay? And after they completely disentangle, we go on to number 4, section in the graph number 4, which is the rubbery flow. And then after the rubbery flow, we have a complete, let's say, slippage between the chains. And then the polymer transforms from a solid to a liquid after passing through the melting point. Okay? That is a modulus versus temperature graph for a semi-crystalline polymer. Let me put it, note it as well. Okay. That are a couple of notes that I mentioned already. Below the glass transition temperature, or no, when we around the glass transition temperature, we have a full rotational freedom of the main chain, okay? We have a change in conformations. We have a segmental motion of the main chain, but in this case, we have still cohesion through the entanglements. So in this region, let's say, cohesion between entanglements remains, okay? And then there is this, the melting point, which is a rubber to fluid transition temperature, which is Tm, this is Tg. This is the melting point where the chains are able to freely move against each other. We have a viscous flow or a liquid flow in general, and we have chain slippage in this region, okay? Chain slip, okay? Simple. Finally, another kind of thing to sum up. In the glassy states, we said the chains are frozen in. The modulus in this case is determined by secondary interactions, okay? And the forces between the chains are intermolecular interactions, so such as hydrogen bonding, dipole-dipole forces, and dispersion forces, such as the London dispersion force, let's say. I think Colin already introduced you to dispersion forces. The London dispersion force is generally, I want you just to remember, it is the weakest intermolecular force. Well, also Colin should have told you that the London force is a temporary attractive force that results when the electrons in two adjacent atoms, okay, occupy positions that make the atoms form temporary dipoles, okay. That's why sometimes the London dispersion force is also called induced dipole attraction. Not important for the concept of not too much important for the concept of this course. Then from the glassy state, we pass on to the rubbery state. We have segmental rotational freedom. We have the chains moving, but still the entanglements haven't, completely disappeared. The chains are entangled but moving. Okay, there is a vibration between the chain. So that is why we have cohesion. And finally, when we provide even more thermal energy, there is enough energy for the chains to move freely and then disentangle between each other. The mobility between the chains is enhanced so much that the chains slip past each other. And let's have a look at this graph, which is a modulus versus temperature graph for two polymers with different characteristics, as you can realize. It is obvious, of course, from the graph. The blue curve shows us a nitrile butadiene rubber that is an elastomer, okay? And we said elastomers display only glass transition because they only have amorphous structure, okay? And we said already that the glass transition is a feature of the amorphous fraction, okay? And then next to NBr, we have polyvinyl chloride, which is, as you can realize, a thermoplastic, a semi-crystalline thermoplastic, which displays both a glass transition temperature, or a glass temperature as it's called, and a melting temperature as well, okay? This is a melting temperature here. It's not important for now. The glass transition, of course, as you can realize, it is a polymer specific, and as I mentioned, the way we experience a polymer depends on its glass transition relative to the room temperature. So you can see here what is very interesting. Here in the glassy region, let's say in this region, still glassy for both materials, which is at very low temperatures. In this case, both polymers have the same modulus, okay? However, when we increase even further the temperature, at -40, we can see that the NBr has a glass transition temperature, okay? So obviously, at -40, the modulus of the NBr drops significantly. The polymer is much softer, okay? It displays its elastomeric characteristics. And that is why when we look at a temperature of room temperature, let's say, or normal temperature, 25 degrees, it should be, I don't know, around here. If we look at 25 degrees, let me use a different color, not to confuse you. What one? Green. So if we look upon 25 degrees, we can see that for 25 degrees, the NBR has much smaller modulus than the PVC, okay? And that is why we experience generally NBR as an elastomeric material, while we experience PVC as a thermoplastic material, a material that it can be, let's say, elongated a bit, but it is much stiffer than an elastomeric material. So the NBR is soft, elastomeric at room temperature, while the PVC displays, let's say, thermoplastic characteristics. So the modulus is much higher. It can be flexible, but of course not overly flexible. Let's say flexible, higher modulus than NBR. Okay, so the way, that's why I mentioned that the way we experience a polymer, the way we understand the properties of a polymer in our real life depends on its glass transition temperature in relation to the room temperature. Okay? And an example is this lock and chain with PVC cover, and this blue thing here is a PVC cover, okay? And this essentially was my own personal lock and chain, which I grew up when I was going to school. I grew up in a mountain region, and it was very cold in winter. And when I was locking my bike, I used to hate this lock and chain. Can anyone realize why did I used to hate this lock and chain when it was winter? Please let me know in the please let me know in the Wicom thing. Why would I hate this lock and chain with this PVC cover when it was winter? I see an answer from Elliot. Another from Zhu. Xingyu. Pronunciation must have been terrible. Sorry about that. Well, yes, absolutely. You got the point. When it was winter and it was very cold outside, this PVC cover was less flexible because the chains were essentially, as we were saying, the chains were the macromolecular chains, right? Not the real chains. The macromolecular chains of the polymer were frozen, okay? They were not able to be extended, to be flexible. So in this case, in order to handle this chain and everything, you need to increase the thermal energy onto the PVC in order to make it soften and in order to make it more flexible, okay? So that is why I say that the way we experience a polymer, it depends on the temperature that we experience a polymer. If it was summer and in Greece, it was like 30 degrees, obviously the behavior of this lock and chain would have been completely different. It would have been much more flexible. But when it was -5 degrees, then the chains did not have enough energy to be flexible, okay? And because of that, it wasn't easy for me to handle this this lock and chain. But of course, the glass transition temperature is not such trivial or such unimportant phenomenon, such as myself being able to unlock my bike. And I'll give you the most characteristic example where the glass transition temperature of a polymer affected significantly a whole space mission. Okay, and let me stop sharing. Give me a second. Share screen. Share. Let me play you a video now. This is the Space Challenger disaster that happened in 1986, okay? And I want you to see what happened there, and then we will discuss about it.
Started. T-minus 21 seconds, and the solid rocket booster engine gimbal now underway. T-minus 15 seconds. T-minus 10, 9, 8, 7, 6. We have main engine start. 4, 3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
Where is liftoff? Oh, what's happening? Sorry, give me a second. Why is this not playing properly? Sorry, just a second. I'll fix it.
SRB hydraulic power units have started. 9.
No, it's not playing. Give me a sec. I'll find it. Open with VLC.
Hydraulic power units have started. T-minus 20.
Where is it? What? Okay. Good. Where is my... Okay, share screen. Challenge and disaster. Share.
Solid rocket booster engine gimbal now underway. T-minus 15 seconds. T-minus 10, 9, 8, 7, 6. We have main engine start. 4, 3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
Roger, roll, Challenger. Good roll program confirmed. Challenger now heading downrange. Engines beginning throttling down now at 94%. Normal throttles for most of the flight, 104%. We'll throttle down to 65% shortly. Engines at 65%, 3 engines running normally, 3 good fuel cells, 3 good APUs. Velocity 2,257 feet per second. Altitude 4.3 nautical miles, downrange distance 3 nautical miles.
So the 25th Space Shuttle mission is now on the way after more delays than NASA cares to count. This morning it looked as though they were not going to be able to get off.
1 minute 15 seconds. Velocity 2,900 feet per second. Altitude 9 nautical miles. Downrange distance 7 nautical miles.
Looks like a couple of the solid rocket boosters blew away from the side of the shuttle in an explosion.
Let me share my normal screen now. It's this one. Share. Okay, so as you can realize, I was telling you, this space mission was delayed for quite a while in the United States, and there were a lot of pressure from the media and the public in order to make this happen. And apparently, the reason for the failure of this mission, and of course the killing of the whole crew of the aircraft, was because they did not take into account that this day, the day that they planned the space shuttle launch, it was a very cold day, okay? And because when you have elastomeric seals, you want them to display elastomeric characteristics. But because it was so cold, the elastomers were very stiff, okay? And because the seals were very stiff, they were not able to seal the fuel from going inside a specific region in the aircraft, and then this disaster stroke. So essentially, that's what I'm saying here. A failure of an O-ring seal was determined to be the cause of space shuttle challenging disaster. Okay. I want you to remember, of course, it also has to do with what we said, that the way we experience a polymer and the properties of the polymer depend fully on the temperature that we experience the polymer. And in this case, because it was very cold, the chains were frozen in, as we say, and the material was very stiff. So essentially, it did not display the seal. In order to have sealing characteristics, we need elastomeric properties. But because it was so cold, the material, the O-ring was displaying glassy properties. Okay, stiff properties, stiff modulus. Yeah, so that's where it happened, and a failure took place here. Here they have the initiation of, let's say, the explosion. And this photo is a photo I took 2 or 3, I don't know, it was 2019, I believe, when I was in Los Angeles, and they have a memorial over there for this space the space shuttle disaster, and with the captain of the crew, who was from Japan, if I'm not mistaken. And this is a very, 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 very important physicist. This is Richard Feynman. From Caltech, who was heading, let's say, a committee that would essentially study why this failure happened. And what he did in front of the committee was essentially put this O-ring. This is the seal. This was the type of seal that they were using, okay? And he put it into very cold water for a while. And then when he took it out, because the material was frozen, essentially, it did not display the elastomeric characteristics that we were saying, okay? Enough history lesson. I just use this example in order to show you that, okay, what we're saying now, it might be trivial or unimportant, but in real life applications, these things are very highly important, okay? So we need to be very, very accurate in controlling such parameters that might be minor when we evaluate them, like in terms of physics, but in real life applications, these are very, very important. Similarly to what we were saying about controlling the molecular weight of, let's say, polycarbonate. We said that for low molecular weight polycarbonate, we can fabricate, let's say, CD disks, okay, compact disks for, I don't know, for your PlayStation games or whatever. But when you have a high molecular weight, you create a material that can withstand impact, okay, and you can use high molecular weight polycarbonate for helmets, which can save your life, okay. So they might be trivial, but they're very, very important in the ultimate application that we're using the polymers. So now, besides the main glass transition, we can also have a secondary glass transition, okay? And the secondary glass transition has to do with the mobility of the side chains or specific groups in the main chain, okay? So the main glass transition, we already said, it has to do with the mobility of the main chain. That's easy to understand. That's very straightforward. In the case of the secondary glass transitions, we have partial mobility of the side chains or specific groups in the main chain. In the case of polycarbonate, the secondary glass transition has to do with the mobility of these methyl groups or the mobility of this carboxyl group in the main chain, okay? And I use the example of polycarbonate now because a secondary glass transition, I want you to remember that a secondary glass transition affects significantly the impact properties. Because the secondary glass transition has to do with the possibility of a polymer to dissipate energy under shock, okay? Shock loading, very fast loading, like that, okay? How do we measure and how do we see a secondary glass transition in a modulus versus temperature graph? That's modulus versus temperature. A secondary glass transition can be seen by a small, let's say, solder here, where we have a small dip in the modulus. But it has nothing to do with the main and very obvious dip in the modulus at the glass transition temperature, okay? That is the beta transition, the secondary transition. The main transition, obviously, you can see it here. It has to do with this very significant reduction of the modulus because we say we still pass from the glassy characteristics to elastomeric characteristics. We will see more about from the DMA, from dynamic mechanical analysis. We, as I said previously, we obtained the graph of modulus versus temperature, but also we obtained this very significant graph of tan delta, okay? That is the damping. Don't worry about it now. I will explain more when we will fully evaluate the dynamic mechanical analysis. Anyway, the tan delta versus temperature graph looks like that, the blue graph here. So you can see that the secondary glass transition is given by a small peak, side peak, or solder peaks as they called. And then we have the main peak in the glass transition region, okay? This is a tan delta versus temperature graph, the blue one, okay? I want you to remember that the secondary glass transition have to do with the vibrations or partial mobility, let's say, of side groups or secondary specific groups in the main chain, and they can affect significantly the impact properties because they can dissipate energy in soak loading. And now let's look a bit onto the molecular background, a bit of more polymer physics, let's say. That should be the final. Let me see. That should be the final thing we will be talking about today. Yeah. So before we start looking a bit more closer to the glass transition, let's again have a discussion about what happens in a molecular scale when a polymer is heating. If we start from 0 Kelvin, okay? At 0 Kelvin, that's the absolute zero, the chains are at absolute rest, okay? We have no thermal motions. Everything in its glassy state, and the chains, as we said, they are completely frozen in. In this case, I want you to remember that the bonding between chains is determined by secondary interaction forces, okay? Hydrogen bonds, intermolecular bonds, and so on. Then, if we increase the temperature, thermal motion increases, and gradually, short part of the chains or side groups obtain some mobility. And that can give secondary transitions, not the main glass transition, that is the secondary transitions. Because, as we said, short part of the chain or side groups, okay? That gives secondary transition. That gives us changes in small changes in the conformation of the chains. Whether this happens is a matter of competition between the thermal energy of a group and its interaction with neighboring groups, okay? And this interaction can be essentially expressed as a potential barrier, which has to overcome in order to realize a change in position. And this barrier essentially is this one, okay? In order for a chain to go from a position 1 and conformation 1 to a conformation 2, we need to overcome this barrier. Okay, and in order to overcome this energy barrier, we need to provide more thermal energy, okay? But since the thermal energy is statistically distributed, thermal energy is not absolutely, we cannot say that it is absolutely identical throughout the whole structure, the whole polymer. A fraction of the groups will be able to overcome this barrier, okay? And this fraction strongly increases when the temperature is raised, okay? So there is a characteristic transition temperature for such a specific molecular motion, and this temperature is called the glass transition temperature, okay? The characteristic time scale of in order to realize this energy barrier is given as a function of this energy barrier. This is the time scale. This is the pre-exponential factor. Which is a constant, and if you need to use this equation, it will be given to you, okay? I shouldn't have used delta U. We said is the energy barrier. T is the temperature, and K is the Boltzmann constant. which is also always provided to you. Okay, so in order to observe this transition, the glass transition, in a characteristic time scale, we need to overcome this energy barrier, and it's given by this equation. This equation is called the Arrhenius equation, proposed by Svante Arrhenius, was in I think it's Dutch. He was Dutch, and essentially, besides the time scale, it's essentially a kind of reaction rate as well. Okay, in order to evaluate when this change will take place. It gives the dependence of the rate constant on the absolute temperature and the activation energy. Yes, we already mentioned all this in the previous slide. Okay. That is the characteristic time scale at glass transition. So the time scale on which significant conformational changes may occur. And obviously, if we have significant conformational changes in the macromolecules of a polymer, the macromolecular chain of a polymer, in this case, we have passing of a polymer from its glassy state to the rubbery state. It's obvious that the time scale is temperature dependent because we see the temperature value here. And conformational changes are also possible at low temperatures, even below the glass transition. But in this case, we have very minor conformational changes that have to do with secondary transitions. Let's look a bit more onto which are the secondary transitions. So we have two different types of secondary transitions. It is the gamma transition and the beta transition. And then we have the glass transition. Secondary transitions, though, are tau gamma and tau beta. Okay? Again, we start from very low temperatures. We increase the thermal energy. We have the first transition when localized bond movements and side chain movements can occur. Okay? That is the gamma transition. And then we have localized motions that involve whole side chain and localized group movements. So this is the beta transition. Okay? So if we have different types of modes in the polymer moving, vibrating as a result of the thermal energy that we're applying, then we have secondary transitions. And then once we have enough thermal energy to allow conformational changes, then we reach the glass transition, where the glass transition leads to a large scale motion. Okay, so we have a large scale coordinated motion of a polymer chain and dramatic change in properties. Okay, so we start again. The gamma transition, we have localized bond movements. So we have bending, stretching, and rocking of the bonds, and side chains also movement, such as side group movements. Okay, and then we increase even further the thermal energy. We have localized motions that involve whole side chain and localized groove movements. So we have a beta transition. The gamma transition is very difficult to be observed experimentally. Because the vibrations that are taking place are very mild, okay? We have a very, very low amount of vibrations between the side groups or some localized bond movements, okay? So because it is so sensitive, it is not easy to observe it experimentally. The beta transition, where we have applied a bit more energy and whole side chain and localized group movements can be seen. So it's generally easier to observe than tau gamma. And you saw it already, so how mild, this is the beta transition. You saw already how mild the beta transition is compared to the glass transition here, okay? And how weak this peak is compared to the main glass transition. So imagine if tau beta is already very weak, tau gamma is almost impossible to observe, okay? And finally, as we said, with more thermal energy, we pass through the glass temperature and we observe the glass transition, which is a very intense transition. We have large-scale coordinated motions, change in the position of the chains and passing through from glassy state to a rubbery state or an elastomeric state. Okay. We will finish here for the day. Thank you very much for your attention. Thank you all for coming. As always, if you have any questions, feel free to send me an email or write in the forum or even text me on WeChat or whatever. And I will see you again tomorrow when we will continue with the characteristics of the glass transition. We will finish the glass transition part and we will talk about a few more other things. See you tomorrow all. Have a good evening.